So my name is Zach Schwierer-Conti, and I'm a research fellow here at the Alan Turing Institute in London. I would also like to introduce the co-organizer and my colleague, Andrea Pizzoferrato, who is a visiting academic here at the Turing. And for those of you who are not familiar with the Turing, this is UK's National Institute for Data Science and AI. On a side note, if you are interested in sharing your work with us in this series as one of the seminars, please do feel free to get in touch with either Andrea or myself. We'd be happy to find a slot that would suit your schedule. Questions may be asked towards the end of the talk, unless our speaker today is okay with questions being asked throughout the talk. And finally, so without further ado, I'll ask my colleague Andrea to introduce the speaker for today. And with that, I thank you all for joining.
Thank you, Zach. So our speaker today is Sascha, who is currently serving as a postdoc at the Technical University of Graz. He holds a bachelor and master's in physics and has completed a PhD entitled Bayesian Uncertainty Quantification of Numerical Simulations of Aortic Dissection at the Graz Center of Computational Engineering. Currently, Sascha's research interests lie at the intersection of uncertainty quantifications of computer simulation, Bayesian machine learning approaches, and the application of these methods in various fields, including biomedical engineering. Motivated by his passion for interdisciplinary research, today Sascha is going to share with us his approach on connecting probability, physics, and neural networks. Without further ado, Sascha, the floor is yours. Thank you again for joining us for this seminar series.
Yeah, thank you, Andrea, for the kind introduction, and thank you both, Zach and Andrea, for the very kind invitation today. I've been following this seminar series for a while, and it's a great honor for me to be the speaker today. And what I'm going to show you today is, Andrea mentioned, so before I was more doing Bayesian probability theory, uncertainty quantification, numerical simulations, stuff like this. And what we're going to talk about today was more like a hobby in the beginning that I kind of dug into, and then I found some interesting relationships between these realms of probability theory, physics, and neural networks that I'm happy to share with you today. So the central question of this, I would say even of this entire seminar series, would be how can we bring physics into machine learning model? And as many of you know, this is a surprisingly hard question. How can a machine learn physics? How can a machine do physics? Turns out to be often surprisingly tough to do this. And there's a number of ways how we can approach this problem. And I'm not climbing an exhaustive list today, but I'm just going to bring up the obvious ways how we can look at this problem. And the first one would be simply through data, right? So a machine learning model can learn physical behavior implicit from the data. And typically for this is large amounts of data necessary. Then it still will not typically generalize in a physically meaningful way outside of the data. But if we have plenty of data, often this is enough. Yeah? Off-the-shelf methods work just as fine if we just have enough data and if it is sufficient for our purpose. Well, another very popular approach is through the loss function. Many people call this physics-informed learning. Other people think of physics-informed learning as a bigger field. Anything where we try to bring physics into a machine learning model is physics-informed. But there's also a narrower sense to it in that we take the following optimization approach. Yeah? So W here would denote the machine learning parameters, weights and biases in a neural network, couple parameters in the Gaussian process, for example. And you optimize with respect to some optimization objective. Very typically, you minimize your data loss or data error. So Y being targets, F evaluated at XD being predictions of a machine learning model evaluated at some pivot points XD. And then you conjointly with that penalize this training or regularize it in some sense with a second term in the loss function where you penalize deviations of your predictions from the physics. Yeah? So This is, in a more narrow sense, what many people understand as a physics-informed learning approach. And what is really nice about this approach is, it's, as you can see, it's comparatively easy to write it down. It's also comparatively easy to write it in terms of codes. Typically, it can be very hard to train. Yeah? And just so you know how I understand this second term here, what we do is, in such an approach, we take a machine learning model F. Okay, we evaluate the prediction. Well, wrong order. We take this ansatz function, we put it into a differential equation that is described by this differential operator O hat. Yeah, so this basically here in the big round bracket is your physical equation, differential equation, for example, such that on the right-hand side is 0. Yeah. So this measures your deviations of your predictions from your physical equations evaluated at some pivot points xp. Yeah, so you do this pointwise. You take some points where you probe the you probe your model against the physics, and you minimize those deviations. So this would be the second term, and this is what I would say in the narrow sense most people think of a physics-informed learning approach. And we will see later that this has lots of benefits. It's very general. Yeah, you can apply it to almost any problem, but it also has some downsides in terms of being can be very difficult to work with this principle. Well, we can also work with what we put into a model. You can work with canonical coordinates, quantities that have physical meaning like symmetry or invariance. So what I mentioned so far is you can mingle with what you have on the output side of your model, like through the loss function, or you can mingle with what you have on the input side, feature engineering. Typically, you can also mix this in any combination you want, basically. But you can also mingle with what you have in between, architecture design, or open the black box. So what I mean really is not just think about how your inputs can be meaningful and how your outputs and your training objectives can be meaningful, but also the inner workings of your machine learning model. And I think today we're going to be focusing more about this latter notion. Well, to introduce it fully, physics-informed learning, the idea is, I mean, I mentioned it already a bit. The idea is we plug some ansatz into a differential equation, and here I really introduce notation, where this O hat is a differential operator that defines a differential equation. It could be a Nabla operator, it could be a Laplace operator, the Lambert operator, it could be more general, something that defines a Navier-Stokes or Maxwell's equation. And I'm introducing this operator because this operator is what I'm going to be using for most of this talk. So we're not going to be too specific about certain operators because we don't have to. Yeah, F is some machine learning ansatz model with input X and machine learning parameters W, and we write it such that the right-hand side be 0. Yeah. And by the way, this operator O hat, this subscript X, the meaning of this is that it acts on the variable X and not on the variable W. Well, this already said, data loss or likelihood in a probabilistic way, and the physics loss can be interpreted as a prior in a Bayesian interpretation, if you will. And one difficulty here is this tuning parameter here. So you have to weigh those losses against each other. Typically, you have more terms. So you typically have to also include initial conditions or boundary conditions. And how you weigh these terms against each other is can be very difficult to do. So let's look at really a numerical example to illustrate what I really mean here. A 1D Helmholtz equation. So in this case, this operator would have this simple form, second derivative with respect to x plus nu squared. So this is a wave number squared. This is a constant. And the true solution to this differential equation here on the right-hand side is the solid black line. A solid black line, okay, very simple. And now we train a physics-informed neural network on this problem. We have two loss terms. The first one is this left-hand side, the noisy observations, white disks. So we learn here from data, plus we minimize the deviations from the physics. So this is the physics laws term, evaluated pointwise on those upside down triangles here. These are the test pivots. And on this we train. And for this plot, I actually already optimized the hyperparameters. Here on the left-hand side, a convergence plot of here in blue, this physics-informed network. We see that, okay, this generalization gap generalizes quite well. We see it here. But convergence is, we need really a lot of training steps here, which is surprising given how simple this problem is. Yeah, it's a very simple problem, but the optimization is really crunching a lot of numbers still. And we will later see is one problem here is that we chose an activation. It doesn't make sense for this problem. So yeah, upside, really simple to code and write down very generally. You can do it for nonlinear equations. Absolutely fantastic approach. But it can also be hard to train even for simple problems. So let's open the black box. And for this, I want to introduce a number of notions that, to me, it seems in this community are not being, not getting a lot of attention, at least not recently. We're gonna build a bridge between physics, Gaussian processes, and you can think of Gaussian processes as a probability distribution over functions and neural networks. And we're gonna use two pivotal, crucial relationships to do this. First, we're gonna build a relationship between physics and Gaussian processes through this relationship here. Yeah? So we have our operator O, and this operator O, this is what defines a differential. It can be a differential operator like Nabla or Laplace operator. It shall be linear. Okay, we're going to talk about this more later. And this operator basically, this encodes the physics, right? If this would be a Laplace operator, then the physics would be a Laplace equation, electrostatics. So this O, operator O, this is the physics. And GP here, this is a notation for a Gaussian process with zero mean and some covariance function K. I will introduce notation later in a bit more detail. And what we find is when you apply such a linear differential operator to a Gaussian process with covariance K, it gives you again a new Gaussian process with a new covariance function K here, where you apply this operator O to the covariance directly. And this equation allows us to establish a link between the differential equation that describes our physics and our Gaussian processes. On the right-hand side, we're going to use another important relationship that some people might call the infinite width correspondence. And what this refers to is that when you take a neural network and you make it very wide, then it turns out it behaves like a Gaussian process again, the covariance function of which is determined by the architecture, and for fixed architecture by the choice of your activation functions. And we're going to use these two to bring all this together. So this slide is for those of you who don't know what is a Gaussian process. It's a probabilistic form of machine learning. You can think of it as a probabilistic kernel machine if you're familiar with that. And the intuition behind this is all of you know what is a Gaussian distribution. You have a mean, you have a variance, and when you generalize this idea to multiple variables, multiple random variables, you call it a multivariate Gauss distribution. You describe this with a mean vector and the covariance matrix. Yeah? This covariance matrix tells you the variance of each variable. It tells you how each variables correlate with each other. And this is not mathematically very rigorous, but it builds intuition. When you generalize this idea further to infinitely many random variables following a Gaussian distribution, then this would be described not with a mean vector, but with a mean function, and not with a covariance matrix, but with a covariance function of two arguments. Typically, you write it like this. A function g of x is distributed according to a Gaussian process with a mean function mu and the covariance function k of x and x prime. And what this already implies is that the Gaussian process is a distribution over functions. Now, there's a very common view a function space view that you understand the Gaussian process as a probability distribution over functions. But the definition is not so much more abstract or complicated really than this. The definition will really be a stochastic process where for every value or combination of x's on the real line have a Gaussian distribution. Like in this little cartoon, g of x is our Gaussian process, this is the real line, and for every point here on the real line, I have a Gaussian. And all those Gaussians are correlated with each other, and how they are correlated with each other, this is basically defined by this covariance function. And this is essentially what you do when you do machine learning with Gaussian processes. Typically, it really boils down to your definition of this covariance function k. Yeah? So this is it's basically the first choice you have to make when you want to learn a Gaussian process from data. Yeah, we can refine this notion of Gaussian process for differential equations. By the way, can you see the title line actually? You can? Good, okay, because I can't. There's some Zoom panel, but it's fine. So let's refine this a bit for differential equations. Let's take a function g distributed like a Gaussian process. Let's take a zero mean prior with some covariance function k of x and x prime. So x is some point on the real line x, and x prime is some other point on the same real line. Yeah? So it comes from the same support domain. Let this be constrained by a differential equation in the following way I have introduced previously. We have some differential operator O hat subscript x applied to some Gaussian process g. So our ansatz function now is this Gaussian process. And for now, we will work with the same example as before, a 1D Helmholtz equation where this operator has this form, second differential with respect to x plus a constant. And now when we apply this operator to a Gaussian process, by linearity, we can show that what comes out of this is again a Gaussian process where this differential operator here is applied twice to our original covariance function. You have to read this in the following way. First, we apply our operator with respect to the first argument x, first argument of k, and then we apply the same operator with respect to the second argument x prime, second argument of k here. So this gives me a new Gaussian process that has this transformed covariance function in a sense. And we can use this to force Gaussian process to obey this differential equation a priori through the construction of an appropriate covariance function. Yeah? And for the above example, the solution is this. So this particular covariance function defines a Gaussian process that fulfills this equation here a priori. And there's a number of ways how you can phrase this. The easiest one is if you view it like this. You take your Gaussian process and you say at points where x equals x prime, your variance, you demand it to be 0. So you have this type of equation here, and when you find a k that is consistent with this equation, then the Gaussian process implied by this covariance is consistent with this equation. So you can find kernels to do this. Yeah, okay, I wanted to bring a side note here. So far we are really limited to linear differential operators, but there's also actually one group, California, working on how this can be generalized to nonlinear PDEs. And another flavor here is a Mercer representation. So it turns out that if it is a kernel of a Gaussian process, then you can represent it in terms of basis functions. Oh, I just see that here's actually this should be a p. Limit p goes to infinity. And I want to note here that this not always has to go to infinity. Sometimes the basis is finite. But you can represent a covariance function k in terms of basis functions phi and some prior covariance matrix M. Yeah? And if it's a kernel, then this representation exists. And these basis functions could, for example, be Green's functions, or it could, for example, also be Gaussian functions. You can try this out when you take phi to be Gaussian functions that are centered on the real line in an equidistant distance to each other, and you weigh it by the distance increment, and you execute this limit, you get a Riemann integral. It gives you the squared exponential kernel. So Gaussian basis functions here would then actually yield the Gaussian kernel on the left-hand side. There's also other basis functions like the cosine that gives you this squared exponential kernel. All right, so Gaussian process kernels can be engineered to be physically consistent. We can think of this idea, and let's look at the numerical example, why and when. This is actually interesting. I wrote down again our simple equation. F is a machine learning model, our Gaussian process with input X and learning parameters W. And what we take is this, this dashed black line is the ground truth, the true solution to this equation. We take two noisy measurements from this, and now we let loose the Gaussian process to learn from this data. We use a vanilla RPF kernel or a squared exponential kernel. This is synonymously called often. And this red solid line, this is the posterior mean. The shaded area is the corresponding uncertainty. What we see is this Gaussian process, it interpolates as expected. It falls back to zero outside of the data is also expected. I used the zero mean prior here. But there's basically no notion of the physics. And this is not surprising, right? It cannot. There's no mechanism in this learning model to learn the physics instead of the data. Hypothetically, if we had lots of data everywhere here along this dashed black line, then this Gaussian process would be doing fine. It would learn this behavior here in between. As soon as we go outside of the data to the left or to the right, it again would be falling back to zero and do not generalize in a physically consistent manner. But we don't have this, so we don't have enough data, and also we actually want to be generalizing in a physically consistent or meaningful way. But let's do the same numerical experiment again with this. I call it the Helmholtz kernel. So I showed it to you before. The Gaussian process implied by this kernel is consistent with this equation a priori, cosinus x minus x prime, and this is the result. So what we see here is that the Gaussian process with this kernel gives faithful predictions in the interpolation regime. It extrapolates, it generalizes in a physically meaningful way. Well, also the uncertainties are quite small with just 2 data points. So what we see here is that in this case, it really pays off to think, what should your kernel look like? How can this kernel make sense with what I know a priori about my system? And it really is interesting when you don't have a lot of data and when you're really interested in physically meaningful models. So Gaussian processes, can we do something similar with neural networks, as I had implied before? And for this, I will first introduce some notation. For now, we will focus on single layer networks. But we're going to discuss a bit more general architectures as well. We got weights and biases, V, W, A, and B. We got an input X. We got some neural activation function H, and we sum over N neurons. Okay. And now let's make the following observation. Wide neural networks behave like Gaussian processes. For this, I showed you the following experiment. First, we take a single layer feed-forward neural network with N neurons. Number N neurons will be a variable. Second, we sample random weights and biases from a Gaussian distribution. Okay, so the V's, the W's, the A's, and B's are now random variables sampled from IIT distributions. And then we collect the predictions at fixed input pairs. And what we see here is, so the top row is a tensions hyperbolicus activation, and the bottom row is a sinus activation. And what we see in each subpanel is on the x-axis, we see the neural network prediction at a fixed input x equals minus 0.2. And on the y-axis, we have a neural network prediction at a fixed input 0.4. It could also be any other two input values for x. And at those two fixed values, we sample weights and biases, and thus we create this scatter plot here. And we do this for, in the first column, n is 1 neuron, not exactly a network, right? Second column, we do it for 3 neurons, and in the third column, we do it for 10 neurons. And what we see as the number of neurons increases is that, by the way, also mind on the top here and on the right flank, we see the marginal histograms of these scatter plots. And what we see is, okay, with very small networks, okay, this does not look Gaussian at all, but when we have 10 neurons here, this very much already behaves like a Gaussian. Which is interesting, right? So just a couple of neurons and really behaves like a Gaussian distribution. And the essential, so we just observe this, but we can also explain this. And the essential mechanism behind this is the central limit theorem. Large sums of random variables become Gaussian. Yeah. Let's look for this. For this, we look at the infinite width limit, n goes to infinity. And you can understand this in the following way. Yeah, we also need some assumptions, of course. This is important. We assume the neurons to be identically and independently distributed. For example, a Gauss. It can also be something else than a Gauss, just not some funny distributions like Cauchy distributions where no second momenta exist. And the second assumption is that the activations be bounded. And what we have here is, so we say that W is a random variable. So are the A's and the B's, and the V's are random variables. This means that this entire term in the sum is also a random variable. And now we sum up, we have a large sum, we sum up many of those random variables. And in the infinite limit, this is the sum of infinitely many IID random variables. This applies the central limit theorem. The central limit theorem tells me exactly, okay, this behaves like a Gaussian. So say W has a Gaussian distribution, or I'll give it a gamma distribution, what you want. You feed it through some activation H, for example, tangent hyperbolicus. This transforms this into some other funny probability distribution. Yeah. But it doesn't matter, as long as we sum up plenty enough of them, the sum F will be distributed like a Gaussian, even if W and H of W times X plus B plus A gives you some non-Gaussian distributions on its own. Now notice that I have made my argument, my reasoning, without mentioning X. So this holds for every X, and this is exactly the definition of a Gaussian process. So this is an intuitive way how you can show that wide neural networks must behave like Gaussian processes. So this confirms or explains our observation. Well, very important, this also works for more general architectures. I would say even indeed for most interesting architectures. And I really can recommend this paper from Greg Yang, who showed that wide feed-forward or recurrent neural networks of any architectures are Gaussian processes. This includes transformers. Yeah? So it's really applicable to a very wide class of architectures. And this is actually a side note, but this infinite limit. So what have we done? We have taken a neural network and we have made it infinitely wide. And from this, we could get some insight. This is a really powerful limit that allows us to understand a lot about neural networks. I give you some examples of what other people already were able to understand from doing this infinite width limit. For example, Yarengar and Zubin Garamani could show that dropout regularization can be understood as a special Bayesian prior when you understand your neural network as a Gaussian process again. So this was one of the first papers. Williams devised what many people call the neural net-induced GP kernels. Jahun Lee showed that it works for deep networks. We saw before that it's now much more general. This proof works for transformers, shown by Ron 2020. Also a very popular is this neural tension kernel. This is actually not really a probabilistic approach, and it's not understanding an infinite neural network as a Gaussian process, but it's doing that in a non-probabilistic way. Charcot understood neural networks as a kernel machine. So he also carried out an infinite limit, but in a deterministic, in a non-probabilistic fashion. So this is also widely considered a very important work. So conversions, diversions. Let's quantify this a bit more. How do these neural networks converge towards a Gaussian? And you can well, this is one way how you can look at it. I'm sure there's many others, but you can compute the Kullback-Leibler divergence D of P against Q, where P is the PDF of the neural network sampled from the weights and biases, and Q is the Gaussian process from the analytically or the estimated kernel of the infinite network. Yeah, so we'll come to that in a minute. For many networks, you can derive the infinite kernel analytically. For some, you have to estimate it. But this also converges reasonably fast typically. And this Kullback-Leibler divergence, dP against Q, it is a measure of how dissimilar the probability distribution P, how dissimilar it is to the probability distribution Q. So what I'm trying to measure here is how un-Gaussian this neural network behaves. So less value of KL divergence is more Gaussian. And we quantified here KL divergence, this measure here, as a function of neural network width. A couple of different experiments. We do it in this panel for ReLU activations, for tangent hyperbolicus activations, for sinus activations, for different depths, for 1 layer blue, 2 layers orange, 3 layers green. And we can see what's interesting here is that so deeper networks seem to require wider structures in order to be to have similar Gaussianity, but the convergence rate, at least heuristically, seems to be similar. Yeah. So I found this interesting. The convergence rate does not significantly change here with depth. All right, so when is this the case? When is a neural network corresponding to a particular Gaussian process? And in principle, this turns out to be a simple thing. In practice, this can be very difficult to compute. On the left-hand side, we have our Gaussian process with kernel K. And on the right-hand side, this is the covariance of the neural network. The pointed brackets here denote an expectation value. Expectation with respect to weights and biases. And when the covariance of the predictions of the neural network, when they are equal, the kernel of the Gaussian process, then the two are equal in the infinite limit if the network truly converges towards the Gaussian process. So we can play around with this a bit. We can insert our infinite neural network here. We can, under certain circumstances, we can exchange the limit with the expectation value. Yeah, so expectation is linear. If this limit is uniformly converging, we can pull through the expectation to the activations here. And you might notice that here with sigma v squared, this is the variance of the prior of the VKs. And same for the sigma b squared, this is the variance of the prior of the b's. And when they are independent, then we can factor it out like this. We have to introduce here a scaling factor where this goes with where this variance goes with 1 over the square root of number of neurons for this to converge. And it all boils down then assuming that the neurons are IID, it all boils down to this term basically. So this is the essential thing that we need. You can call it the covariance of the neural activation functions. This is what we need to care about. And if this covariance of the neural activation functions, if this matches with the covariance function or the kernel of your Gaussian process, then this is indeed the neural network that matches this Gaussian process and vice versa. Good. Another perspective is here on the left-hand side. I mentioned it before briefly. The left-hand side, we can still represent this kernel through its Mercer representation. Yeah, and if we want, yeah. So if it's a kernel, then this Mercer representation exists, and we can write it down like this. This time I put the correct symbol for the limit here. If this is indeed an infinite basis, where phi were basis functions, m some prior covariance matrix. But this I find this relation really interesting because it really gives you, when you choose these basis functions to be Green's functions, it gives you a relation between the Green functions, between your physics and your neural activation covariance. All right, this I already said. So you can take this prior diagonal matrix to be diagonal. You have to shrink your priors and your weights and biases. You have to shrink them very small, and then you find that your activations have to match those basis functions. H have to match activations. H have to match basis functions phi. Okay, and we can play around with this also in a slightly different fashion, the following way. So cast it into two simple forms that we need to remember. The first one is, this is the condition for equivalence. Yeah? So if the infinite network converges towards a Gaussian process, then the covariance of the infinite neural network defines the kernel of the corresponding Gauss process. And I mentioned it briefly in the beginning of my talk when I was still talking about Gaussian processes mostly. We have this condition for physics consistency. Yeah. So applying our differential operator twice to the covariance function k, this gives me a condition when a Gaussian process is physically consistent with what I know. And now we can plug in this formulation into this formulation. We can multiply it out, rearrange the terms a bit, and can find this lengthy expression. So this is really just writing everything out. And when the limit is under some nice conditions, I will come to this in a minute, you can pull your differential operators through your limits, through your expectation, and apply them directly to your activations. So what you get is differentiated activations. And you get this condition for physics consistency of a neural network. So yeah, I promised this. I'm going to talk briefly about the switching limit integral and also switching differential and the limit especially. So this is mostly harmless. It turns out it is. Actually, this is not peer reviewed yet, so I encourage you to distrust me at this point. But it seems that we don't need a lot of assumptions in order to be allowed to make these exchanges between limits, expectations, and differentials. Basically, so we have this theorem that the series of differentiated functions and the differential of the series of the function converges to the same limit, and under these assumptions you can do this exchange. And I did not find a pathological example yet. I'm pretty sure that there is examples where you are not allowed to do this. But it seems that for many problems this is possible, or at least there is a fix how you can do this. Yeah, and under these assumptions, then you can actually show that the neural network with these differentiated activations here in the infinite limit converges towards a Gaussian process with your kernel being defined or being implied actually by these the covariance of these differentiated activations. Yeah, so neural networks are Gaussian processes. Gaussian processes are neural networks. It really seems to me difficult to pick a side here. What is better? We can switch between the realms and have different perspectives on more or less the same object, not entirely, right? So we will always work with finite networks in practice, but at least for the infinite networks, we can really understand something, and we can construct an infinite network that is consistent with your networks, and then you can relax those assumptions. You can relax. Gaussian processes are really nice. We know a lot about them. We really handle the maths, but we also assume smoothness and Gaussianity. And in an infinite neural network, relaxing this assumption basically really means you go back from infinity, you go back to a finite network. You relax smoothness assumptions, you relax Gaussianity assumptions. You lose tractability, but you get this little extra capacity that you need. Yeah, so we introduced, these are the two important relationships. A linear differential operator applied to a Gaussian process gives you a new Gaussian process, and infinite neural networks behave like Gaussian processes. I briefly mentioned this Mercer representation of the kernel, and you might argue that this actually gives you even a direct link between a neural network and your differential equation, if you will. You don't necessarily need your Gaussian process or your kernel space, reproducing kernel Hilbert space, to establish this link. You can view it also for the basis functions. So 1 and 2 equals 3. Gaussian process kernels can be engineered physically consistent. Wide neural networks behave like Gaussian process. So can we engineer wide neural networks to inherit this physically consistent property, at least approximately? And I will fall back on the similar example as before, this very simple numerically 1D Helmholtz equation. And it seems a Gaussian process, actually it's the other way around. The Gaussian process, a neural network implies a Gaussian process. Sometimes we can go into the reverse direction, not always, but sometimes. So for certain differential equations, this neural network for a certain differential equation implies a Gaussian process for a certain differential equation. And sometimes this can also go, we can also go in the other round, the other way. So we had this equation on the left, the covariance of the Gauss process, on the right-hand side, the covariance of the neural activations. We can use the left-hand side to encode physics into a Gaussian process, and thus, by matching activations to be consistent with this equation, we can code physics into a network by finding activations H such and pairs of priors and activations such that this is consistent. So I already said this on the. Remember from before, the kernel that implies a Gaussian process that is a priori consistent with a 1D Helmholtz equation has this form, cosine x minus x prime. Now it turns out on the right-hand side, it's very simple to find activations that are consistent with this kernel in the infinite width limit under Gaussian IID priors and the weights and biases. And it's really just this. You need a trigonometric activation functions, and that will be a neural network that in the infinite limit is consistent with this kernel and thus consistent with our differential equation. Yeah. Yeah, and you can give names to this Helmholtz covariance or Helmholtz kernel or Helmholtz activation. I'm just thinking that this helps in giving a name to this. Yeah, so the name comes obviously from the name of the equation. So numerical example. I've briefly shown you this at the beginning of this talk. The solid black line is the ground truth to our Helmholtz equation. we get 10 noisy data points, the white disks here. We got, for later, we got upside down triangles, pivot points where we can probe deviations from the physics. And we're gonna test this with 3 different neural networks, simple ones. The first one is a vanilla data-driven only network. In green, single layer segment activation. Very simple, just as simple as that. They're the simplest neural network that you can think of. And we try to learn from the data. So this data-driven only network only learns from those 10, or is it 11, 1, 2, 10 data points. And what we see, okay, interpolates nicely here. It does some overfitting here. So we should have stopped training probably a bit earlier. We can also see this here in the convergence plot. Solid line is training error, dashed line is testing error. We see a large, for the data-driven vanilla network, a large generalization gap here. And we can also see in the solution, as soon as we go away from the data, this data-driven approach generalizes into the universe. So there's no notion of physics in there, and that's not surprising because we have not built in any mechanism to generalize there. How can it actually be? Especially also because we chose an activation function that doesn't really make sense. Well, the second approach, physics informed, we do the same, but now we introduce a physics loss regularizer. So we evaluate the physics laws, the deviations from the physics pointwise at those upside down triangles, and we use this to regularize the training. We see the blue dotted curve. Okay, we get a nice physical extrapolation here. If we go farther away from the data, then it might deteriorate, and convergence is okay. Even for a simple problem, lots of numbers crunching here. Surprising. Well, not when you think of the sigmoid activation functions are really not a good choice here, but it is a default choice, right? So I wouldn't say that any other default choice of activations would be so much better in this example. Well, and in yet another approach, you might call it physics consistent. It's again the same thing, but we only do a tiny little difference. We use an activation that has been derived from the theoretical considerations that I have just presented to you in the past 40 minutes or so. And what we see is, okay, it generalizes nicely, just like the physics informed neural network generalizes well. It's physically meaningful, but just that it trains much faster, it converges much faster. So it seems that putting your thoughts into how you can bake your prior physics knowledge into your model, be it the Gaussian process as kernel as we saw in the beginning, or the neural network, the activation, the architecture, can really give you a benefit and save you a lot of headache of time in the training. Well, limitations. I'm about to come to an end. Limitations. This is, I would say, very important because there's some very severe limitations to this approach. The first one is that we can only look at linear constraints to preserve the Gaussian process property. So I introduced this relationship here in the beginning. It really hinges on linearity. If this differential operator is non-linear, then this Gaussian process is not a Gaussian process anymore. It transforms the Gaussian process in a way that is not Gaussian anymore. And to give you an example, Navier-Stokes. So Navier-Stokes that includes the convection term. The convection term is the non-linear part typically in the Navier-Stokes equation. Will basically kill this approach. But of course, if you linearize and neglect convection, then you can go back again to this in principle. So this is a severe limitation. But you can at least conceive that the generalization to piecewise linearity is possible. I don't know, this is really speculation, but there is actually this paper from Humanawadi and Amber Stewart from California, where they employ Gaussian processes also for nonlinear PDEs for kind of a piecewise. Everything that is nonlinear, you can approximate it for piecewise linear functions, right? So this could be an approach. I don't know, yeah. So until at this point, this is speculation. Another important limitation is that this is a hard graph. It's difficult to find these architectures. It's difficult to find these activations, these priors. It's really not simple. It's, as I said in the beginning, this physics-informed approach where you write down this physics laws. This is easy to write down. It's easy to code, but difficult to optimize. In this notion here, it's exactly the opposite. It's very difficult to write it down, but once you have written it down, the optimization becomes much easier, typically. Yeah, well, at least as is suggested from this experiment. So, and of course, this becomes more difficult with increasing complexity of your neural network architecture and of your PDE. Yeah? So, but the upside is you have to only do it once, right? So, normal neural networks, you have to train it again and again for new problems. But once you have figured out how, for a certain physically prior knowledge, your corresponding architecture or your corresponding kernel activation must look like, you have it. You can take it off the shelf from then on. But getting there is difficult. Good. I should wrap up. Conclusion. I think there's one important message here, that is a physics-consistent neural network implies a physics-consistent infinite neural network. Implies a physics-consistent Gaussian process, and in some cases vice versa. And we can code prior physics knowledge into the kernel or the activation of our models. We can't go beyond the loss function. This can be very difficult, but it can also be very rewarding. Here's my reference. There's also a nervous workshop paper where this is boiled down into a bit of a shorter version. I want to acknowledge all my supporters, funding agencies in Austria, especially also Graz Center for Machine Learning, which was a great supporting infrastructure for my research. And yeah, of course, I thank you for your attention, and thank you again so much for the invitation. It was a great pleasure.
Thank you very much. Thanks a lot for your interesting observations. I'll open the floor to questions. We have one comment in the chat, and I'll read it out to you. It's from Isatao. An important limitation on physics-informed machine learning data acquisition and benchmarking. In many problems where the physics-informed machine learning architecture is applicable, the right data are simply not available. Much work has generated models capable of learning general solutions from sparse and incomplete data. Do you have, it's more of a comment than a question.
Yeah, it's more of a comment, yeah. The right data. Would the one asking the question or the comment can speak up?
So we have.
Yeah, if you can hear me.
Yes.
So I wanted to ask. Obviously, with the Helmholtz problem, like it's kind of it's a good example to find these activation functions that are consistent. Did you try to, in a sense, I don't know how to put it, like text the counter hypothesis of, in general, just something that is oscillatory? Like, for example, do they work the same if you have like a cosine of you have like some combination of other like oscillatory, not necessarily like sinusoidal functions?
Yeah, this is actually a good question. So there is, I didn't say this very expressly, but there is, this is not necessarily unique. Yeah. So I will give you an example with the kernel. What we need is that the kernel in the limit is physically consistent. And I say this briefly: when you take Gaussian basis functions and when you in the Mercer representation, and then you take the limit, this gives you a squared exponential kernel. But if you know the random, this one famous paper, random Fourier features, it's maybe 15 years old, so it's very famous, random Fourier features. They did something very similar. They used cosines and sinuses. And their combination also gives a squared exponential kernel, as you can show in this Mercer representation. Yeah, so it's not the same as what I'm showing here, but it is absolutely not surprising if this is not unique, and multiple activations would be consistent with the same kernel. So I did actually do other experiments with Bessel functions for another reason, and there I saw, okay, this does not typically work so well. But the Bessel functions cannot be completely compared to sinusoidal or cosinusoidal test functions. I think that to really round up on this question, I hope that this answers satisfyingly. Say you take another periodic function like a zigzag. Okay, this will also be periodic. I don't think that this would work very well, because it gives you periodicity, but this kernel would not be, I'm pretty sure it would not be consistent with the corresponding Gaussian process kernel. Is it answered satisfyingly?
Yeah, I would say so. Yeah, I've been wondering in general about the connections. Like I did spend a bit of time thinking about like the whole like siren stuff and Fourier features and like representations like that. Kind of well, if I might like add another one, if no one is if not, I can ask again later.
Oh, well, I have time, but I guess the chair has to.
Yes, a quick one. we have 3 questions in the queue.
Yeah, it's kind of like a follow-up on it in a sense. If the activation functions are in a sense like useful if they are consistent with the kernel, would that mean that, for example, putting PDEs in like frequency space could mean that having in a sense how would I put it, like neuron activations that are basically like Fourier components, would that be kind of like equivalent in the sense that you will be giving possibly a representation? It's probably over, I don't know if under or over determined, but like would that be a valid representation for a PD in the frequency domain, for example?
So first I have to say, I don't know, because I didn't try it, but I think it's a very valid question, and I think it's a very promising way to go, because I don't see any obstacle why all these considerations that I had today, why we should not do this in Fourier space. I don't see a principal obstacle why we should not do all of this in Fourier space. Yeah.
Awesome. Thanks a lot.
But I don't know. I guess we have to try. Yeah?
Thank you very much. So next is Jake. Go ahead, Jake.
Thanks, Zach. And thank you for the talk. It was great. My question is somewhat related. If the previous question was on uniqueness of the activation functions associated with the PDE, my question's on necessary and sufficient conditions for them to exist. Like, so on slide 14, you mentioned some assumptions about the kernel, but then on slide 17, you sort of show, slide 14, assumption is bounded, slide 17, but also it works for ReLU. Do we know for like a linear, in general, for a linear PDE, is it guaranteed that there is an activation function that represents that encodes the Gaussian, the appropriate physics Gaussian kernel?
Yeah. So for a general linear PDE, first, well, there's actually a number of answers there. So it actually turns out you can do it for a linear PDE with constant coefficients. You can do this kernel. So the Gaussian process kernel is much easier. And for linear PDEs with constant coefficients, this usually exists. So I'm sure you can come up with some funny pathological examples where it don't, but there generally this exists. For the neural activations, I don't know all yet. Yeah, I would even go as far as to say I don't think so. Actually, I would be surprised if it really works for every. Well, I have one thing in mind, but it's not published yet, so it doesn't make sense to comment on this this detail. So I cannot give you a 100% answer. Yeah, so I believe that there's examples where it does not exist. For many interesting examples, it does exist. I really have to do more research to 100% understand really the most basic requirements for their existence. Yeah? So I'm very sorry. Maybe in 2 years I can tell you precisely.
Yeah, well, thank you. I appreciate it. I'll stay attentive if I hear you giving a talk in a year or so then.
Yeah. So I'm working, what I can say is I'm working on this, yeah. Yeah, period.
Yeah, very cool. Thank you.
Thanks, Jake. Manish?
Hi, thank you so much for the talk. It was really informative and your insights. My question is around, you mentioned that for Gaussian processes, we have a greater depth of knowledge. Is there some other real-world applications you can give with this approach that connects physics, Gaussian processes, and neural networks?
Yes. Well, yes and no again. So, you can do this physically consistent kernels even for Maxwell's equations. So you can do this for really meaningful, interesting physical equations. You can find kernels that are consistent with the physics, and it turns out that, well, also this is, I mean, I'm working on it. It's not peer-reviewed yet, so I encourage you to distrust me here. But it looks like this example of Maxwell's kernel, if you want to call it like that, you can do a similar thing with the activations.
Okay.
But again, maybe in 1 or 2 years when the paper is out, really, it's not period. Please caution, yeah, distrust me here. But for the kernel Gaussian, for the kernel, Maxwell's equations are perfectly feasible, yeah.
Okay, thank you.
Thank you very much. Daniel next.
Yes, thank you for the talk. It's more of a clarification about how physics consistent Gaussian processes work. So we basically solve an equation where we have a kernel applied to the left-hand side of PD equals 0. So for example, when I think of a GPU of RBF, it has some support, right? It has some functions it can learn. I would expect linear PDEs to have, you know, a very constrained set of solutions. When you do this, when we make a GPU physically consistent, are we saying that it on averages follow the PDE, or all samples of the GPU follow the PDE? That's something I'm not entirely sure about.
Yeah, that's also a good question. In this sense, how I formulate it, but I mean, you can formulate it in a different way, yeah. But in this sense, every realization would be consistent at the points where you observe.
I see.
But there's other ways to make Gaussian processes physically consistent, right? So there's actually really this is just one way how you can think of it. But there is, for example, I've seen approaches where people would do it approximately from Anders Solin, if you're interested in Aalto University, I think he is. I was doing this approximately through Fourier expansions of the like, yeah.
Yeah, I was thinking about I think on latent force models, right? I think they on average follow the differential equation, but yeah, I was just wondering for this specific approach.
I encourage you to look at this through this lens. I don't know, but it looks it is absolute to me. It seems absolutely reasonable. This can have a lot of advantage because it's maybe less strict and less stiff, and then it might be easier to come to terms with something at the expense maybe for something else. Yeah.
Yeah. Okay, yeah, that makes sense. Thank you.
You're welcome. Thank you.
Thank you. So I have a question, but I can wait till the end. Jake, go ahead.
Thanks, Zach. Yeah, so another question here, if you can, is for a data assimilation problem where your x's aren't known, where they may be normally distributed. Do those conditions about being a kernel when you're now sort of multiplying in another Gaussian distribution, does that still hold? Can you still do this with a data assimilation approach?
To be honest, I don't think I understood the question. Do you mean when you multiply a Gaussian process with another Gaussian process?
Yes, I guess that is what I'm asking.
So when you multiply two Gaussian processes with each other, what you get is something that is certainly not a Gaussian process.
Right. Okay.
So we basically we can go home at this point. I mean, of course, you can say, okay, we have. I mean, think of it as a square of a Gaussian process. It's certainly not Gaussian, okay? But then you say, okay, I want to somehow approximate it again with another Gaussian to fall back on this. Could be feasible. I don't know. Yeah. So certainly you will have to introduce another approximation here because a product of two Gaussians is not a Gaussian.
Okay. Thank you. That helps.
Thank you, Jake. So I'll ask my question. And I would not like to keep everyone on the call. So when you talk about physics consistency, I imagine you assume that here there's an assumption being made that the physics you're supplying, in this case, the differential equation in the kernel, is very well specified. What happens when you're modeling observed systems where you have misspecified physics? So how well specified does the physics have to be for you to reach a generalization that is acceptable?
This is also a good question. Also, this I don't know. Yeah, it's I have to do the research to give this answer. I have to. I mean, you have very clearly defined, or you have very, very clearly understood that I have assumed a rather precise definition of my physical knowledge. That I know these parameters. Can you generalize this? I guess so, because well, it's not a definite answer, but I want to give you an example that gives us a notion here. I showed you this differential operator, second differential with respect to x plus some constant. The constant didn't matter. So I just say there's a constant, it's a wave number squared, but I never really needed to know that this value, to come to the conclusion what kind of structure I need to be consistent with this. I don't think that this is a definite answer to your question. I think there's lots of work to be done in this direction, but I think there's some capability of coping with not precisely known parameters in these different equations. But it also would go a bit beyond further, right? So this model misspecification problem, yeah, it's important. I agree with you.
Yeah, I think this links to a bit of a more philosophical discussion that maybe we don't have capacity for now, but it's certainly yeah, your reply sort of is already indicative of certain directions. So thank you. Okay, I'm conscious of the time, and I would not like to keep everyone on the call. If there's no other burning question, I guess we can call it a day.
Is the question of ISA2 answered?
Oh yeah, that's right. Yeah,
he put the comment in the chat.
Is ISA2 still on the chat on the call?
If you want, you can drop me an email, of course, anytime.
Thank you. All right. I'd like to say thank you to you, Sascha, for sharing your work with us today and your observations. And thank you
for the invitation.
Pleasure. Thank you to everyone for joining and for all the really interesting questions. We'll see you again in our next seminar. Thank you all.
Thanks again, Sascha.
Thanks all for your interest. Goodbye. Drop an email anytime.
Thank you.